is Dr. Sridhar, back to you with another video session on synchronous machines. And in today's video session, we are going to discuss about principle of operation of synchronous machines. Those are also called as alternators. And what are the types of rotors is nothing but how many types of alternators are there and what are their specifications along with its applications. And in continuation to that, we are also going to discuss about the induced EMF expression and how much of EMF it will be generated in the armature conductors. So let us start with the overview of alternators. Alternators are nothing but synchronous machines. First, why that alternator is called as synchronous machine? Because this is a machine, unlike induction motor, it always rotates at synchronous speed. Synchronous speed is nothing but that is 120 times of frequency to number of poles. So always the rotor of this alternator rotates at synchronous speed. But whereas in the induction motor, in the three-phase induction motor, always the rotor will be behind the synchronous speed. It always try to reach the synchronous speed, but never it succeeds. That is the magic that will happen in the induction motor. But whereas in the synchronous machine, in the alternator, the rotor of this alternator or synchronous machine always rotates at synchronous speed. That we can easily calculate how much of synchronous speed. What is the synchronous speed? Synchronous speed is nothing but 120 times of frequency to number of poles. Like this, we can easily calculate the speed of rotation of that rotor of alternator. So here it depends on supply frequency as well as it depends on the number of magnetic poles. So these alternators are also sometimes based on the requirements, based on the application in which area exactly we are using these alternators. These alternators can be classified based on the position of armature windings and the field windings. Suppose if the field windings are kept on the starter, this is the one type of classification. And instead of this, if the field windings are kept on the rotor, this is the another classification. So based on these two things, these alternators or synchronous machines can be classified as rotating armature type. Rotating armature type means field is indirectly, it was placed on the starter frame, and on the rotor frame armature conductors will be placed. Generally this type of configuration it will be used at low power applications, because now this is a three-phase alternator. Three-phase alternator means maximum amount of output that machine has to run. Suppose in the power plants, if you could see in the power plants also that majorly the generating elements or generating machines are nothing but the alternators or synchronous machines only. So this synchronous machine has to drive that much of load, means because of the rotation only, because the development of induced EMF in the armature, it depends on the armature conductors and how much of magnetic field that will be there between the starter terminals. So these are the major parameters. These highly influence the induced EMF it will be generated inside the armature conductors. If the armature rotates or it is able to reach its maximum speed within a fraction of seconds, then we can drive that load, that huge amount of load that will be placed across the armature terminals very easily. So that's why better that loading can be done on the starter frame, because armature conductors, if it instead of rotor, if the armature conductors are placed in the starter frame, this we can easily drive, because you need not spend maximum amount of energy to overcome the moment of inertia of the rotor to bring the rotor to a rotor synchronous speed. So that is the logic behind this. So there are two types of armatures are there, or two types of alternators are there. That is rotating armature type and rotating field type. So suppose if the field are placed on the armature and if it is rotated, armature is nothing but it is a rotor. If the field is placed on the rotor, if the rotor is rotated, then it is very easy, because armature is nothing but that is a seat for generation of electrical energy. So better as much of less weight if we could place on the rotor, so we can easily attain the rated speed within a shortest period, and we can easily overcome the moment of inertia. So for larger applications, this rotating field type synchronous machine is always preferable. But in the standard nomenclature, rotating armature type, rotating rotor type is a preferable one. But for larger applications, better maintain the stationary armature. That is the logic here. In rotating armature type, the armature winding is one on the rotor and the field winding is on the starter. Just now we have discussed about this. The generated EMF or current is brought to the load via the slip rings. These type of generators are built only in small units. In case of rotating field type generators, these are used at larger power rating applications, and the induced EMF it will be generated. You need not spend slip rings also not required, because rotating field type generators, the slip rings it will be used for the excitation, and for the collecting of the electrical energy we are going to collect it from the starter terminals. So slip rings are not required for the collection, but whereas for excitation to the rotor terminals, now slip rings are required. So coming to the construction, so what is the major thing? Now here one thing we have to remember that this alternator and our synchronous machine or synchronous generator is more or less same as a DC generator. As we discussed so many things related to the DC generators in the previous videos, kindly refer those videos. Those videos definitely will helpful for us for better understanding of this alternator. Only the thing is, in the DC machine, across the armature, the generated voltage is alternating in the nature only, but that will be converted by using a commutator. Suppose in the DC machine or for the DC generator, if the commutator is not there, then the output will become a alternating quantity. So same thing, same for magnetic poles and placing of the armature conductors, everything is same, but let us let us eliminate or let us ignore the commutator segments in that machine, in the DC machine, then that will become more or less as a alternator. So that thing let us keep in our mind. So definitely that will helpful for better understanding of this synchronous generator. The main components of this alternator or synchronous generator are rotor and starter. The starter is a stationary part of the rotor, and the rotor is the component that rotates inside the starter. So always a rotor is nothing but, because already we in the beginning of today's video session we stated very clearly that in the conventional alternator always rotor, now that is a place for keeping the armature conductors. Now that is the body always rotates inside the starter. Starter is meant for the field windings only. Now this exactly I am mentioning these points for conventional machines. In special cases, if you want to drive larger voltage application, larger rated electrical appliances, in that cases, rotating field type alternators are preferable. But in the conventional machines, always rotor is going to accommodate the armature conductors. That is a device always it rotates inside the starter. So the rotor is located on the starter shaft, and the series of the electromagnets are arranged in the cylinder using the rotor or rotating to create a magnetic field. So of course, this is very clear to everyone that how that excitation will helpful for us, and how that voltage it will be supplied for the field windings for the excitation purpose. And based on the types of the rotors, these alternators or synchronous generators have been classified into two things. One is a salient pole alternator, next one is a cylindrical pole or non-salient pole type of alternator. Now, more exactly, if you could observe based on the applications where these salient pole alternators are used, where this non-salient or cylindrical type of alternators are used. The salient pole is nothing but, in its name only, the poles are, that magnetic poles are nothing but projected type. These will be projected outward, which means the poles of the rotor are projecting outward from the center of the rotor, because in its name only it was clearly mentioned that salient poles. So poles are nothing but it is just like projecting type outside the rotor. So into the outer surface, these poles will be projected. There is a field winding on the rotor, because for the excitation compulsory we require field windings. For this field windings, we will use DC supply for excitation. When we pass the current through this field winding, north and south poles will be induced. Because based on the direction of this current, we can interchange the north and south poles. Now, if we could interchange that magnetic poles, so proportionally the rotating direction of your rotor will also change. It means the direction of that magnetic field will also change. So the salient rotors are unbalanced, so the speeds are restricted, because salient type of thing means in the majority of the cases because of centrifugal forces or because of surface tangential forces. So sometimes what happens, there may be a misbalance may be taken place in the salient pole alternator. So that's why there is a speed constraint, because you cannot rotate always the salient pole rotor for longer times at rated speeds, because there may be some different types of forces the conductors will experience, and outer surface projective type magnetic poles also experience. So in view of that, now there is a speed restriction that salient pole synchronous machines will suffer. So generally the preferable speed is 120 to 400 RPM approximately. So these type of machines are wound with concentrated field windings. This is a very important point. So what type of field windings are used? Now concentrated type of field windings it will be used. And where exactly these type of salient pole alternators are used means in diesel engines, in hydraulic turbines. So this is about salient pole machines. Next one is a cylindrical type machine or non-salient pole machine. These machines are having cylindrical, that is nothing but a smooth rotor outer surface. So, and what type of windings? So, in the previous salient pole, concentrated winding we have used, and this concentrated winding also creates some imbalance on the rotor, because all the winding terminals it will be placed concentratedly in one segment only, in one location only. That may also leads to unbalance in the rotor. But whereas here in the cylindrical type rotor, the windings are nothing but the distributed field windings, and evenly that field windings are distributed in the slots of the periphery. The rotor is used for high speed because the rotor is highly balanced. Because of this, there is no speed limit, speed restriction that rotor is suffering. So that's why this is approximately 1500 to 3000 RPM. Up to that speed also, without any hazardous, we can run the alternator. So that is a very important point. This rotor is made up of steel radial cylinders having the number of slots. In these slots, just now also we have discussed about this. It is a smooth surface. Now that outer periphery is going to divide into number of slots and wedges. So in that slots, we are going to place the conductors, field conductors. So this is mechanically robust and flux distribution is uniform. So operates at high speeds and produces very low noise, because there are no such type of projecting type poles are there. So because of this, there is no hissing noise. So very calmly the rotor or this alternator will run. That is nothing but the cylindrical type rotor. And where exactly this will be used, in especially in the in the thermal power plants, these are highly used. That is nothing but the steam turbines. So next one is, what is the working principle of the synchronous machine? The working principle of an alternator is very simple, because it is just like a DC generator. Now only the commutator it will be missed in the DC generator. So we are going to get alternator, but only the thing is a DC generator, there we are going to get single phase kind of alternating voltage across the armature. Here like that we had to keep three windings with a mechanical or with a physical displacement of 120 degrees with each other. Then every 120 degrees phase displaced armature winding will produce one alternating voltage like that. Now the total space have been divided into three segments. Every segment is separated with 120 degrees with each other. So 120, 120, 120. So three different types of voltages we can develop inside the armature. So that is nothing but the three-phase supply. So like that, we are going to discuss about the working principle of this alternator. So only the thing is, more exactly, we had to separate the armature conductors, and there must be a time lag of 120 degrees due to the space displacement arrangement 120 degrees between them. This is a very important point. And you can also see here ABCD conductor, and if there is no commutator segment, so you can easily get this single phase alternating voltage across the armature. So here also we have clearly indicated what is the direction of the current and what is the direction of flux. So finally we can get this. But such type of this, if we are going to place in 120 degrees phase difference in the armature, so finally we are going to get voltage across the armature like this. So this is red color is nothing but is starting with 0 degrees, and this blue line is nothing but the leading voltage. And if you are extending this, now it will touch the reference axis at 120 degrees behind this 0, and next one is nothing but that this yellow is nothing but the 120 degrees lagging. So like this, only the 120 degrees, like that, if you could maintain the distribution, the space distribution of the armature windings in the armature or in the rotor, so you can easily produce three-phase alternating voltage. So this is about the simple working principle of this synchronous machine. So we have discussed so many things about applications, construction, and principle of operation. And the major point, the major element in the alternator is nothing but the armature windings, because armature windings are the windings. With the help of them only, we are going to get the induced EMF. That induced EMF, it will be communicated to the local loads. So that's why. So let us briefly talk few things about this armature windings. What type of armature windings we can come across? So majorly, as we discussed, lap winding and wave winding and mush winding, anyhow it will be there. And one unique type of winding we can observe in these alternators, which is nothing but based on the pitch of the coil. Pitch is nothing but that is the distance between two adjacent coils. Suppose if any conductor, and this is one conductor, this is one conductor influenced with north pole, and another conductor if it is influenced with the south pole, and if these are separated with some 180 degrees electrical displacements, this is called as the full pitched coils. So these two coils are nothing but the full pitched. So the two conductors influenced by two opposite type of magnetic poles. So suppose if this is a conductor influenced with the north, and if this is another conductor, and these two are connected back to back, then this is the another conductor influenced with the south pole. And if the electrical separation between them is 180 degrees, and if these two conductors are joined together, this is nothing but the full pitched coil. Now in this full pitched coil, now there are some harmonic issues. So in that cases, what happens? Now for the better optimization, now generally short pitched windings are used. So what do you mean by short pitched coil? So instead of 180 degrees, this may be reduced by 15 degrees or 7.5 degrees or 20 degrees based on the requirement. So they will not maintain 180 degrees as exactly. That will be, if it is less than 180 degrees, those are nothing but short pitched windings. So like this, based on the pitch of the coil, these armature windings or these rotor windings of this alternator can be classified into two things. One is the full pitched windings, and next one is the short pitched windings. So one more classification based on the number of layers. Already we have discussed about this single layer or double layer type of armature windings. But out of these, all this classification, this full pitched winding and short pitched windings are very, very important. So coming to this EMF equation, because already we have studied about the principle of operation and we have discussed about the armature windings. Now what exactly, how much of EMF, that is the induced EMF, it will be available across the armature conductors, that we are going to discuss now. So there are some standard nomenclature we used to assume for what is that flux per pole in Weber. P is nothing but the number of poles, Ns is nothing but the synchronous speed in RPM, F is equal to frequency of induced EMF in Hertz, and Z is equal to total number of starter conductors, and Z phase is nothing but the conductors available for one phase, and T phase is nothing but the number of turns per one phase. So only the thing here it is, now so far we have discussed about the EMF equation of alternator, I mean to say single phase transformer and other DC generators, DC motors. There only we have discussed up to Z, because there are no per phase quantities are available, but here it is a three-phase machine. So three-phase machine means that armature conductors, as per our just recent discussion, the total armature conductors we have to divide into three phases. So that's why we are clearly mentioning how many number of conductors it will be available per phase, and like that how many number of turns it will be available per phase. So those are nothing but the Z phase and T phase. So assuming, so here in this one we are assuming concentrated type winding. This is a very, very important, because in the distributed windings, if it is distributed, so what type of distribution it is it short pitched coil or full pitched coil? If it is full pitched coil, okay, 180 degrees. If it is a short pitched coil, now how much exactly, 150 degrees or 165, like that. So there will be a constraint here. So let me assume first, after that we will go for the distributed winding. Let me assume first concentrated winding. Now here it is considering one conductor placed in a slot. So all the number of windings it will be placed in one slot. So let us assume for our simplification only one conductor is placed in a slot. So the average value of EMF induced in a conductor is nothing but, as per Faraday's laws of electromagnetic induction, this is nothing but the N into d phi by dt. So rate of change of flux linkages. So anyhow, this rate of change of flux linkages, how many number of conductors we are assuming just now? Only one. So N will become 1. So average value of induced EMF in one conductor is equal to d phi by dt. So for one revolution of a conductor, E average per conductor. So for one revolution, how much of time it will be taken? So anyhow, we know the average value. So E average is nothing but per one conductor is equal to flux cut in one revolution to time taken for one revolution. So what about the total flux? Total flux is nothing but one pair of poles is capable to produce pi. So like that, how many number of pair of poles are there? So that much of flux it will be, it is going to cut in the space or in the air gap. So that's why this is nothing but the total flux cut in one revolution is nothing but the pi into P. So next one is in the denominator, time taken for one revolution is there. So how much of time? So that is nothing but the 60 by N. Why? Because N is nothing but the revolutions per minute. So how much of second? In 1 second, how time taken for one revolution, how much of seconds it is going to take place, revolutions per minute, reciprocal of this, that is nothing but 1 by n minutes. So into seconds means 60 by n seconds. So E average per conductor is equal to, so total flux cutting divided by the time taken to complete one revolution. So pi p by 60 by n. So that is nothing but pi p ns by 60. Because why we have taken ns means, so the rotating speed is nothing but synchronous speed. So straight away we can take pi p ns by 60. So ns is nothing but that is again 120 by 120 f by p. So pp gets cancelled, 120 and 60 is there. So this will be 120 by 60 is equal to. So here that ns is nothing but 120 into f by p. Let us substitute this. Now straight away we can get 2f into pi. So this is nothing but the E average per one conductor. Substituting in this above equation, so let us substitute this value in this particular equation. So we are going to get 2 times of flux into frequency. So this much of voltage, this is the average voltage per one conductor. So assume here full pitch winding, because it is not a distributed one, only concentrated winding. So let us assume it is a full pitch winding. For simplicity, this conductor is connected, as we know that what exactly full pitch winding. So if the electrical separation is 180 degrees, then these two conductors will form 1 turn. That is also very important. So EMF per 1 turn. Now here this is nothing but per one conductor. So like that, per 1 turn, how many number of conductors will be there? So in 1 turn, there will be 2 number of conductors. So 2 into EMF per 1 conductor is equal to 4 into F into pi volts. So already we know that that is nothing but the E average. So E average means we had to convert that one into RMS values. So only the thing is nothing but we had to multiply with 1.11. So because that is nothing but the form factor. So let us multiply that average value with the form factor 1.11. So finally we are going to get E per phase, that is induced EMF in per one phase is equal to 4.44 pi f into t phase volts. So this is nothing but the induced EMF generated in the alternator. So there are so many conditions you can take, because T phase we have assumed, because number of turns per one phase. So number of turns per phase is nothing but T phase is equal. Suppose if you want to convert that one into the to the conductors directly, then Z phase by 2 it will be T phase, or else you can cross multiply this also. So in practice, alternator will have short pitch windings, and hence coil span will not be 180 degrees, but 1 or 2 slots shorter than the full pitch coils. So this is the simplest EMF equation. So like this, we have studied in this today's video session about the construction details, the types of the rotors, and a brief overview of the alternator, and next EMF equation and armature windings. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.